Hi everyone, welcome to section 9.5 where we take a close look at a new type of function. The functions we'll be examining here are called absolute value functions. So in order to determine that we're actually looking at an absolute value function, you're going to see an equation with absolute value symbols in it. So to explore how these graphs behave, we're going to sketch y equals the absolute value of x. We're going to make this first sketch by hand. We're going to draw up a table of values, and then we're going to plot the points on a grid. In order to sketch this graph and build a proper table of values, just be mindful that we want to make sure we see a few things. When you build your own table of values and you're not really sure what kind of graph you're going to get, what you want to make sure of is that you have positive values of x, you have negative values of x, and you choose x equals 0. We'll get into finding intercepts and things like that as we work further into sketching these graphs. But in terms of extremes, I don't like to go too terribly extreme when I build a table, so I might choose values like x equals -5. When I choose a value like x equals -5, we'll show you in just a second how to determine your y value overall. But we also want to pick a few more negatives. So you might have, let's say, -3 as an x value, -2 as an x value, -1 as an x value, and then we go into the positives, and I might choose 0, 1, 2, 3, and maybe even +5. So I'm going to extend this table of values just a little bit. So when you build this table, what you might find is you get some extreme points that you don't necessarily want to graph, but you can still leave them on your table. Right next to this table, I'm going to do the scrap work for calculations. So if we start with x equals -5, then we get y equals the absolute value of -5. And if we simplify that, we know the absolute value of -5 means how many jumps away are you from 0 if you're on the number line. So what we know in this case is that y equals +5. So that's going to be our first coordinate when x is -5, y is +5. We can keep going and doing our calculations down this table. So if we have y equals the absolute value of -3, the absolute value of -3 we know is just +3. So we can fill that into the table. This is going to go nice and quick. So if y is equal to the absolute value of -2, so let's say x were -2, the distance between -2 and 0, or the number of jumps, is just +2, so we're filling in this table rather quickly as we go. If we have y equals the absolute value of -1, again, we're just substituting these values in for x one at a time, we'd get y equals +1. If we have an x value of 0, then y equals the absolute value of 0, and that's still just 0. And as we move into the positives, this is nice and quick as well. So if we have y equals the absolute value of 1, the distance or number of jumps between 1 and 0 is still just 1. So we know the absolute value of 1 is still +1. The absolute value of 2 is +2. So we can, again, we're just doing scrap work here. The absolute value of 3 is +3, and the absolute value of 5 is +5. So we have a whole bunch of coordinates that are going to be suitable to sketch the graph and get a good idea of how the absolute value of x behaves. Now, anytime you build a proper graph, you want to make sure that you have your axes labeled and you have a scale so we know what you're counting by. And I'm going to include all of the points that we found on the table just because we've got the space for it. So when x is -5, we know your y value is +5, so we're going to plot a point there, as long as I pick the right one here. Now, when x is -3, your y value is +3. I'm just counting by ones as you see these ticks. So when x is -3, y is +3. When x is -2, y is +2. When x is -1, y is +1. And we pass through the origin, so 0, 0. To continue plotting those points on the positive side, when x is 1, y is +1. When x is 2, y is +2. When x is 3, y is +3. And when x is 5, y is also +5. So if we were to connect these dots now and create the graph that y equals the absolute value of x is depicting, what you would notice is that it's actually a V-shaped graph. So I'm going to do my best to connect these dots with a nice straight line here for you. And what you see here is a representation for an absolute value function. Now, y equals the absolute value of x will traditionally look like this until we start to make what we call transformations. So a transformation is really an alteration of the graph or an alteration of this function. The translations that we're going to be looking at, or the transformations that we're going to be looking at, include horizontal and vertical shifts. So we're going to show you how to move this graph sideways, so left or right. We're also going to show you how to shift this graph up or down. We're also going to entertain what we call reflections. So when we talk about a reflection, basically we're talking about creating a mirror image, and we're going to be creating mirror images across the x or y axis. So if you could imagine folding your graph along the x-axis and imprinting your graph on the other side of the x-axis, we would be talking about some sort of reflection. So we're moving your graph left and right and doing translations. We are reflecting your graph across an axis, either X or Y. And lastly, we'll be talking about what we call vertical stretches or shrinks. So this is either the widening of that V-shaped graph or the narrowing of that V-shaped graph. So let's take a look at how some of these transformations can be explored. This screen is asking us to explore different sketches of graphs and see how those changes to the actual function impact the graph's behavior. The first thing I want you to sketch or to graph on your calculator is a graph of y equals the absolute value of x, and we've done that sketch by hand already. But we also want to graph y equals the absolute value of x plus 3, and we're going to see how these two graphs compare.
So in order to graph an absolute value symbol, you need to explore your math keys. So on the left-hand side of your button options, you'll see a math key under your green alpha key. So when you click on math, or when you hit that key, arrow over once. So instead of highlighting math at the top, you are highlighting NUM for numbers. Now, the first option here in that numbers option is ABS for absolute value. So select option 1 so you can click enter or press number 1. And what it will do is retrieve those absolute value symbols for you. If you have a different kind of calculator, it will say ABS with a bracket. As long as you close the bracket after the absolute value symbol, you'll be graphing exactly the same thing. So we have the absolute value of x in order to graph. And again, if your calculator doesn't default give you these symbols, you will have ABS and then a bracket. You will put X inside a bracket and then close that bracket. So if we were just to graph the absolute value of X, that's the graph that we just created or sketched by hand. The second graph we want you to graph simultaneously is y equals the absolute value. So again, go to math, arrow over to the right so that you are highlighting numbers, and choose option 1, ABS for absolute. So we've got x plus 3 inside those absolute value symbols, and when we graph, we see that it's another V-shaped graph, but it has been shifted. What I want you to pay close attention to is the number of spaces that we have shifted to the left. So here we've got 1, 2, 3 spaces to the left, but our equation was x plus 3 inside those absolute value symbols. We'll come back to that and make a good and proper notation about those changes here in just a moment.
So to document those changes, I've sketched a graph on our regular slides here. So we've got y equals the absolute value of x plus 3. And what we note is that this graph has been shifted horizontally. So we've moved this graph horizontally to the left by 3 units. And that will be important when we start to make other comparisons. So the next comparison we actually want you to make using your calculator is the graph of y equals the absolute value of x and y equals the absolute value of x minus 5. I won't take you through the calculator exercise anymore. You've already got y equals the absolute value of x plus 3 on your calculator. All you need to do is change that plus 3 to a minus 5 and make sure you're using subtraction symbols here. But if you were to graph y equals the absolute value of x minus 5 to see what that looks like, what I hope you recognize is that the very bottom of your V, which we can call the vertex, moves over from center, from the origin, 5 units to the right. So your sketch should look something like this. So if I were to create that V-shaped graph, it would be shifted to the right by 5 units when we compare it against y equals the absolute value of x. So once again, I want you to note that this is shifted horizontally. So we have a left-right type of movement happening here with these changes. And in this case, it's actually right by 5 units. So what I hope you're starting to do is see the link between the equations themselves and how it impacts the behavior of the graph. What we have at the bottom of your screen is a little bit of a conclusion, and sometimes the conclusion at first read is a little confusing. So what we're saying here is that if h is greater than 0, then y equals the absolute value of x minus h indicates a translation of h units to the right. If you have y equals x plus h, it indicates a translation of h units to the left. So what I like to say is that these kinds of transformations are essentially backwards to logic. Normally you think plus means right and minus means left. Horizontal changes or horizontal translations like this are backwards logically. So if I were to give you a new equation, using this kind of logic, if we were to sketch the graph of y equals the absolute value of x plus 9 as an example, because this is a horizontal change, I've changed the x value inside those absolute value symbols. Because this is a horizontal change, I need to think sort of backwards to logic. So instead of plus 9 representing that I've moved to the right 9 units, this actually shows a transformation to the left of that many units. So my transformation, again, is horizontal. And we've moved to the left, whoopsie here, by 9 units. So in these kinds of situations, again, pay close attention to where those numeric changes have been made. In this case, or in these cases, we are changing what is inside the absolute value symbols. And when you change what's inside the absolute value symbols this way by adding or subtracting an h value, you're creating what we call a horizontal shift. So if changing what is inside those absolute value symbols creates a horizontal shift left or right, we want you to start recognizing that putting numbers in different spots in your equation can change your graph in different ways. So now we want to sketch the graph of y equals the absolute value of x and compare it with y equals the absolute value of x plus 3. Again, graph those two simultaneously and make a quick sketch. I'll do the same. Once you're happy with your sketch, sketch another set. So compare y equals the absolute value of x with y equals the absolute value of x minus 5. And we can draw some conclusions about how these modifications change the behavior of your graph. So if we were to sketch the graph compared to what you see on your calculator of y equals the absolute value of x, so you're going to close that absolute value symbol and then have plus 3 outside of those absolute value symbols or outside of that bracket for the absolute value. What you would recognize is that this graph of y equals the absolute value of x has been moved up by 3 units. So instead of having a vertex at the origin, that vertex is sitting at 0, 3 and again opening upwards. So this is a rough sketch of what you should see on your calculator screen when you graph y equals the absolute value of x plus 3. So again, recognize that the plus 3 is sitting outside of those absolute value symbols. So this is what we call a vertical change or vertical transformation. And in this case, amount and direction are important, and we would say it's by 3 units upwards. If you were to sketch the next graph, y equals the absolute value of x and then minus 5, you need to make sure you're using a subtraction symbol here. If you use a negative symbol, it'll actually multiply by -5 instead of subtract. But again, what you'll notice when you compare with y equals the absolute value of x is this graph has been dropped by 5 units. So my vertex, or the low part of that V, is now sitting at 0, -5. So this would be a real quick sketch of what that graph would look like. Again, this is a vertical transformation by 5 units downwards. What I hope you're starting to recognize is that the location of these numbers and where we add or subtract them really impacts the behavior of the graph. And the conclusion we want you to draw is that we've now introduced something called a k-value. A k-value is something that you add or subtract or tack on to the end of an equation. Please recognize that this is outside of your absolute value symbols. So if you have y equals the absolute value of x plus some k-value, this is logical. Plus means up. And if you have y equals the absolute value of x minus some k-value, it means you're going to move downwards by k units. So without even graphing on our calculators, if I said graph y equals the absolute value of x, let's say minus 2, we know that's a regular V-shaped graph that has been dropped by 2 units from its original vertex at the origin. So we could very quickly make a rough sketch here and say this is what our function ultimately would look like. So again, we've gone through horizontal changes that happen inside those absolute value symbols, and we've gone through vertical changes which are impacted by adding or subtracting numbers outside of those absolute value symbols, or you can say you're tacking a number onto the end of the equation. What we'd like to do now is put some of this into practice. So the first example asks you to describe the changes to the graph of y equals the absolute value of x that result from the change in each of the following equations. So basically what we're saying is if you start with y equals the absolute value of x, and instead of that equation, you now graph y equals the absolute value of x plus 3, all minus 4, what kind of changes have you made? Not only that, but where is the new vertex of our graph? Now, the original function y equals absolute value of x has a vertex at 0, 0. So any horizontal and vertical change will impact the location of that vertex. So let's take a look at what's happening inside those absolute value symbols. If I see the absolute value of x plus 3, that's like saying x plus h. This is a horizontal change. And what I want you to remember is that horizontal changes are sort of backwards to logic. Plus 3 actually means we have moved this to the left by 3 units. Now, aside from that, we see that a number has been subtracted from the end of an equation. So this minus 4 is actually a vertical change. So instead of thinking about, being backwards, logically speaking, vertical changes are always logical. Minus means down, plus means up. So we have moved this whole graph down by 4 units. So if I start with a vertex at 0, 0, and if it helps you to draw a little grid, that's great. If I start at 0, 0, and I move to the left 3, so here's 1, 2, 3 units to the left, and I move down 4, 1, 2, 3, 4, there's my new vertex. So I've moved left 3 and down 4. If I want to note the coordinate of that new vertex, I know it's going to be at -3 for an x value and -4 for a y value. So that's the new location of my vertex based on those transformations. Now in part B, we start with an equation that looks slightly different. This is y minus 7 equals the absolute value of x. What I'd like to remind you is that if you're ever to graph a function or you want to analyze the graph of a function, it needs to be in the form y equals. So what we want to do is actually add 7 to both sides, but when we add 7, we're not going to add it inside those absolute value symbols. We actually have to add it to the end of the equation. We can't just absorb that in our absolute value symbols. Now that we have this rewritten, what we recognize is there was no change in x, there was no horizontal change that was made. This plus 7 is happening at the end of the equation. So this is noting that there has been a vertical change, and in this case we know plus means up, so we would say this is up by 5 units. So again, if we were to start with a quick sketch and our vertex at the origin, and we just moved that vertex, or sorry, not up 5, my goodness, that's incorrect. Let's fix our numbers here. It's not up by 5, we know it's up by 7. My apologies for that. So if we start at 0, 0 and we add 7 or move upwards 7 units, 1, 2, 3, 4, 5, 6, 7, here we go. There's our new vertex, and it would open upwards still, but our location of that vertex is going to be at the ordered pair 0, 7. So again, that type of change shifted our vertex up by 7 units. In part C, you have y equals the absolute value of x plus 6. Again, this is not a change in the absolute value of x, it's a change after the fact. So this plus 6 is another vertical change, and we know this is up by 6 units. So we don't necessarily have to draw the sketch every time, but instead of being at 0, 0 for our vertex, we are shifting off the origin by 6 units upwards. So the new location of our vertex in this case is going to be at 0, positive 6. Again, you can confirm all of these by graphing, but analyzing the equation becomes the most important element in this section. The last one we have to do here says y equals the absolute value of x minus 2 plus 1. So there have been 2 changes made here. There's a change inside those absolute value symbols, so it's a change in x. We know that this is horizontal, and horizontal changes are backwards. So minus 2 actually means to the right by 2 units. The plus 1 at the end of our equation is a vertical change, and it's logical, so we say this goes up by 1 unit. The new location of our vertex is going to move in the same fashion. So if we move from 0, 0 to the right 2, our x value is going to be at positive 2. And if we move from 0, 0 up 1, our y value is going to be at positive 1. But again, if a sketch is helpful here, you're welcome to do so. So aside from focusing on vertical and horizontal translations, what we want to do is talk about something called a reflection. A reflection is essentially creating a mirror image, and we're going to create that mirror image either across the x-axis or the y-axis. So in order to explore this behavior a little bit more, we've got some other sets of graphs to compare. So I'm going to pull up our calculator screen here and graph y equals the absolute value of x and y equals negative the absolute value of x. So we're just going to put a negative sign in front of that absolute value symbol. We're also going to sketch y equals the absolute value of x plus 3 and compare it to y equals negative the absolute value of x plus 3. And we're going to explore the changes that ensue.
So if we graph that original function y equals the absolute value of x and compare it with y equals negative, so make sure you're using that negative symbol and not a minus symbol. So we've got the negative symbol, and then we want to retrieve that absolute value. So math, arrow over to number, choose option 1 for absolute. This time we've got negative absolute value of x. When we hit graph, we see that you have two V shapes, but one of them is opening upwards and the other is opening downwards. So if we compare those table of values, we see that for y1, your values are all positive, but for y2, you have the same values, but they are negative. So what we've done is we've created a mirror image across that x-axis. So if you could imagine folding your page along the x-axis, the blue and the red graphs would overlap perfectly. The next graph we want you to compare to see if it holds true is y equals the absolute value of x plus 3. So I'm just going to insert a little plus 3 here. And then we want you to compare that with y equals negative the absolute value of x plus 3. So plus 3 traditionally inside those absolute value symbols would mean we've moved it to the left by 3 units. So let's take a look at these two graphs. What we notice is that the vertex has been shifted to the left by 3 units for both of these graphs, but when we have a negative in front of that absolute value symbol, once again it creates a reflection or a mirror image across that x-axis. When we check out the table of values here, we notice the same thing. All of your y values are positive for y1, which was your original function, and when we reflect that function across the x-axis, all of your y values then become negative. So these are illustrations of reflections, and we're going to go back and just refine this information in our notes to make sure it's 100% clear how these types of reflections have been made.
So a quick sketch of what we saw on our calculator screen. If y equals the absolute value of x is the upwards opening V-shaped graph, and y equals negative the absolute value of x is the downwards opening V-shaped graph, we notice once again that the vertex is in the same spot, but those y values are complete opposites. So in conclusion, we say that if you have a negative in front of that absolute value symbol, what you're going to create is a reflection across the x-axis. The next sketches we want to explore are the graphs of y equals the absolute value of x with y equals the absolute value of negative x. So this time that negative symbol needs to be on the inside. Once we compare those sketches, we're going to take a look at another set, but I want you to make a little editorial change here. This second function needs to be y equals the absolute value of negative x plus 3 without those brackets in them. So if we were to sketch y equals the absolute value of x plus 3 and y equals the absolute value of negative x plus 3, we're going to notice a different type of change. So we're going to graph these two sets and explore reflections in a very different way.
So the first set of graphs we want to compare now are the absolute value of x and the absolute value of negative x. So when we hit graph this first time around, what we recognize is the blue and the red graphs are actually identical. If we look at that table of values, we see that for every x value, the y value for the first function, or y1, is exactly the same as the y value for the second function. So basically, these two functions are identical. If we take a closer look at our picture, I hope you can imagine if we were to fold this graph along that y-axis, the two graphs would be overlapping perfectly. So what we've created here is a different type of reflection. We didn't create a mirror image across the x-axis. In this case, we created a mirror image across that y-axis. And all of that is because of the location of that negative sign. So let's see if it holds up when we have some horizontal changes as well. So if we were to graph y equals the absolute value of x plus 3, and compare that to y equals negative, or the absolute value of negative x plus 3. Again, this time those negative symbols are inside those absolute values. We can hit graph and see, in fact, the same thing sort of happens. We're creating mirror images, but this time we're creating mirror images across that y-axis instead. So again, if you can imagine folding your graph along the y-axis, those two graphs would be overlapping perfectly. So once again, this is a reflection across y instead of a reflection across x.
So once again, in conclusion, If you have y equals the absolute value of negative x with that negative inside those absolute value symbols, this is a reflection across the y-axis. So we're creating a mirror image across y.
So our last set of transformations has us comparing y equals the absolute value of x with a numeric value in front of or being multiplied by that absolute value symbol. So we're comparing with 3 times the absolute value of x. So you want to put 3 in front of that retrieval for absolute value. So we've got 3 times the absolute value of x. And if we hit graph, remember the blue graph is going to be our regular absolute value function. And 3 times the absolute value of x is going to be the red graph. So let's see what happens here. What we notice is they're both V-shaped graphs with their vertex in the same spot, but the red graph, so 3 times the absolute value of x, is much narrower in shape. If we compare your values on the table, we've got a y value of 4, let's say, to start our table off. But when we graph 3 times the absolute value of x, it's actually going to triple the y value. So instead of a y value of 4, it's 4 times 3, or 12. Again, we can see that's holding true for all of these ordered pairs. We can see when x is 3, my y1 value is 3, but my y2 value, or my narrower version of this absolute value function, is 3 times that. So 3 times 3 would be 9. Now, if we wanted to graph our third function and sort of make a prediction here, we've got 1/2, so we can go 1 divided by 2 times the absolute value of x. So math, choose option 1 for absolute value of x. And when we graph all 3 of them simultaneously, what we recognize is that your third graph, 1/2 times the absolute value of x, is now much wider than your standard absolute value function. And if we look at your y values, because we've gone from a y value that triples, so if we compare our y1 value with 4 and our y2 value of 12, we tripled that y value because it was 3 times the absolute value of x. It makes perfect sense that our y3 value is half the original y1. So for half of 4, we know is 2. We could say half of 6, of course, would be 3. We can compare all these things on the table and make perfect sense of why our y values are so much smaller, because they're in fact half of their original y's. So what we're doing with this last set of transformations, if we go back to the picture, is we're not changing the vertex per se. What we're doing is we're creating a wider or a narrower graph. So what you can predict is that if you have values in front of that absolute value symbol, is going to impact how wide or how narrow that V shape is going to be seen.
The conclusion we want to draw now is that if you have a coefficient or a number sitting in front of that absolute value symbol, so we'll denote that as a times the absolute value of x, that a value will make the graph wider or narrower depending on its value. So if that value happens to be greater than 1, but we actually say the absolute value of a being greater than 1, because if we have a negative in front, it's actually a reflection. It doesn't change the overall width of the graph. But if we say that the absolute value of a is something bigger than 1, we have what's called a vertical stretch. And a vertical stretch means that your graph is getting narrower. So the graph of y equals 3 times the absolute value of x is negative, or is narrower than the original y equals absolute value of x. If that value of a, or the magnitude of a, is somewhere between 0 and 1, so we say things like 1/2 or 2/3 or 3/4, then what that implies is there's been a vertical shrink. And a vertical shrink means that your graph is actually getting wider instead of narrower. So those are the two changes that have been imposed when we multiply the absolute value of x by a specific value. So just a quick recap, we have had in this particular module, horizontal changes. So we say that could be something like x plus or minus h. We've had vertical changes, so that's the absolute value of x plus some value k at the end of your function. We've had reflections, so we had negative the absolute value of x. We've had a different type of reflection, so absolute value of negative x is a different type of reflection. And now we've had an a value. So a constitutes a stretch or a shrink when we're talking about vertical stretches or shrinks, which again changes how wide or how narrow the graph is. So when I go back and really classify these changes more carefully, we want you to note that horizontal changes are always backwards to logic. If you are adding an h value, it means you're going left. If you're subtracting an h value, it means you're going right. So these are your horizontal changes. If you add or subtract a k value, that's a vertical change. So instead of moving left or right, we're going to be changing or repositioning your graph upwards or downwards. Those vertical changes are always logical. So plus means up and minus means down. If you see a negative in front of the absolute value symbol, this is a reflection, as we've noted, but you have to be very careful about which axis. So this is a reflection across the x-axis. So you've created a mirror image and a V-shaped graph that's opening downwards. If you have the absolute value with the negative inside, you've got a reflection across the y-axis instead. So again, that's creating a mirror image across the y-axis. And last but not least, we have a vertical stretch or shrink, and that is going to make your graph wider or narrower by a factor of a. So please have a look at the homework questions that you see at the very bottom of your screen. Let's clear this out so you can see them carefully. Please have a look at your homework questions and do some practice with these transformations, because we're going to utilize these transformations with different functions moving forward. As always, if you have any questions, don't be afraid to reach out and let us know.